Hello and welcome to Shri Tech Education YouTube video channel. In today's lecture, we will study how to find the natural frequency of free torsional vibration by one derivation, and we will study one of the numerical based on that. Now, in previous lecture, we have already discussed that when the particles of shaft or disk move in a circle about the axis of shaft, then the vibrations are known as torsional vibration. In this diagram also I have shown one disc attached to one shaft at the bottom and it is fixed at one end. When that disc is twisted in one of the direction, let it be clockwise or anti-clockwise with some angle theta, then it will oscillate about its mean position by angle theta clockwise anti-clockwise continuously. That type of vibration about its axis is called as a torsional vibration. Now in this case the shaft is twisted and untwisted alternately and the torsional shear stresses are induced in the shaft. Torsional vibrations may result in the shaft from the following forces in many applications. These forces may be inertia forces of reciprocating mechanisms such as pistons in IC engine. Inertia forces of reciprocating mechanisms will result in the torsional vibration. Impulsive loads occurring during a normal machine cycle, for example during operations of a punching press. Shock loads applied to electrical machineries. Torques related to gear tooth meshing frequencies, turbine blade passing frequencies. Now during these all forces acting on the system, there is a torsional vibration occurring. Now one example I have shown one vibration in two rotor system in cases where two rotors are mounted on a shaft and one tends to rotate in clockwise, another tends to rotate in anti-clockwise direction. There is possibility of twisting and untwisting of that shaft in opposite directions. This will cause the torsional vibration inducing in that shaft. Now in some cases of IC engine, in the piston or in the connecting rods, there is continuously acting some forces. These forces are called as reciprocating forces or inertia forces acting on that will also result in the torsional vibrations. Now one more example, alternate twisting and untwisting of shaft and disc, two rotor systems for these mechanisms as well as for the mechanisms having massive rotors and flexible shafts. In that case also, in that rotors or shafts, torsional vibrations are inducing. Now it is more necessary or most important to calculate the natural frequency of these free torsional vibrations, because whenever these external forces acting on these shafts exceeds beyond this natural frequency of torsional vibration, then there may be chances of failure of the system. Therefore first we need to calculate these natural frequencies and then we can apply up to that natural frequency the forcing frequency. So we will calculate first the natural frequency of free torsional vibration. Now consider again a shaft of negligible mass whose one end is fixed and at the other end it carries a disk of weight W. Now that shaft of negligible mass has some stiffness. That stiffness we will call it as a Q torsional stiffness in Newton meter. Let theta be the angular displacement of the shaft from the mean position after time t in radian. M be the mass of the disc. I be the mass moment of inertia of the disc in kg meter square. I is equal to mk square, where m is mass and k is radius of gyration of that disc in meters. Now if suppose I rotate that disc in any one of the directions, let it clockwise or anti-clockwise, by some angle theta and then release, then that disc will twist and untwist continuously, which results in the torsional vibration. Now during that we will calculate the natural frequency of this torsional vibration. But before that, I will remind you, in case of longitudinal vibration and transverse vibration, we have found the natural frequency with the help of three methods. In longitudinal vibration video, we have seen all these three methods in detail. In transverse vibration, we have derived the frequency by using equilibrium method only. But the three basic methods available to find out the natural frequency are equilibrium method, energy method, and release method. Now we are using here equilibrium method to find out the natural frequency of torsional vibration. To study previous these all methods, watch the video given in the description, or one link is given at the top right corner as suggestion link. Click on that link and watch the video to study equilibrium method, energy method, and release method in detail. Now here, if that disc is twisted and untwisted, there may be one accelerating force and one restoring force acting on that disc or shaft. Now that restoring force is equal to minus q into theta. Now that q is torsional stiffness of the shaft and theta is angular displacement. In case of longitudinal vibration, we have seen there restoring force is equal to k into x, where k is a stiffness of the spring and x is the displacement, linear displacement of that spring and mass. Now here, instead of that stiffness k, we are using the torsional stiffness q, and instead of x linear displacement, we are using here theta angular displacement. This is the restoring force which opposes the accelerating force. Now what is the accelerating force? Now here, mass moment of inertia into acceleration. Previously, in case of longitudinal vibration, we have seen that accelerating force is equal to mass into acceleration, that is m into d2x by dt square. But here in case of torsional vibration, it is mass moment of inertia into acceleration, that is accelerating force is equal to I into d2 theta by dt square, because here theta is the angular displacement, that's why its acceleration will be d2 theta by dt square. Now equating these two equations, we will get one equation, one differential equation, one simplified differential equation, that is equation number 3, d2 theta by dt square plus q by I into theta is equal to 0. Now observe carefully, in case of longitudinal vibration or transverse vibration, we have got same type of equation, and that is d2x by dt square plus k by m into x is equal to 0. Here instead of x it is theta, and instead of k it is q, instead of mass m it is I moment of inertia. Just these representative values are changed because of torsional vibration, because of angular displacement. Now this third equation is now very much similar to the fundamental equation of simple harmonic motion, because this motion of clockwise and anti-clockwise, that is twisting and untwisting of that disc, is very much similar to the simple harmonic motion. Therefore we'll compare it with the standard equation of SHM, and that is d2 theta by dt square plus omega square into x is equal to 0, or there may be omega square into theta is equal to 0. Now compare that third and fourth equation, we will get omega is equal to square root q by I, because here instead of omega square, here q by I is there, therefore omega is equal to square root q by I. This will be omega. Now we know the time period of SHM is equal to 2 pi upon omega. Put the value of omega here, we will get time period Tp as 2 pi into square root I by q. Put this value of time period in the formula of natural frequency. We know that natural frequency is equal to reciprocal of time period, whereas time period we have found here is 2 pi into square root I by q. Therefore frequency Fn is equal to 1 upon twice pi square root q by I. That is the formula for natural frequency of torsional vibration, where Fn is the natural frequency, Q is the torsional stiffness of the shaft in Newton meter, and I is the mass moment of inertia of the disc that we can find out by mk square, where m is mass of the disc and k is the radius of gyration of that disc. This is the natural frequency of torsional vibration. Now, from in this natural frequency of torsional vibration Fn, we can simplify same formula little bit later like this. The value of this torsional stiffness Q can be found from the torsional equation, and that equation we are knowing that tau by J is equal to G theta by L. Tau by J is equal to G theta by L, where tau is the torque applied, J is the polar moment of inertia of the shaft, and that can be given as pi by 32 d raised to 4, where d is the diameter of shaft. G is equal to modulus of rigidity of the shaft material, theta is equal to angle of twist given to disc, L is the length of shaft. Now from this formula, tau by J is equal to G theta by L, we can find out tau by theta value. Tau by theta is equal to Gj by L, that we have got. Now here tau by theta is nothing but torque given to that disc by that much angle, by theta angle, will give you the stiffness of that material or the stiffness of that shaft or disc. Therefore Q is equal to tau by theta and is equal to Gj by L. That's why I can write Q is equal to Gj by L. Now put this value of Q in equation of frequency, we will get Fn is equal to 1 upon twice pi into square root Gj by I into L, because value of Q we have put as Gj by L. Fn is equal to 1 upon twice pi square root Gj by L into I. Now this is the formula for finding natural frequency of torsional vibration in the system. Now we will find out the torsional vibration of single rotor system, two rotor system and three rotor system, because there may be chances of producing torsional vibration with the help of single rotor on single shaft, two rotors on the single shaft, that we have shown here one example. Two rotors are there attached at the two ends of that shaft. There may be chance that one more rotor can be attached on that shaft at the center. It will create a three rotor system. Now with the help of that, these cases we have to find out the free torsional vibration, natural frequency of this free torsional vibration of single rotor system, double rotor system and three rotor system. Now for the single rotor system, whatever formula we have generated or derived previously, that is for one shaft and one disc attached to that, same formula will be applicable for the single rotor system. For a shaft of negligible mass whose one end is fixed and another end is carrying a rotor, the natural frequency will be Fn is equal to 1 upon twice pi square root Q by I, or it is equal to 1 upon twice pi into square root Gj by L into I. Now in that formula or in that diagram, one more diagram at the bottom I have drawn, and that is called as amplitude of vibration of torsional vibration A at the end of this cantilever. At the end where one rotor is attached, rotor B is attached, suppose, at that rotor there will be torsional vibration maximum. That's why maximum amplitude I have shown that A, small a, where at point A there will not be any vibration. That's why that point I will call it as a node point. Therefore in note what I have given, read that note, the section of shaft whose amplitude of torsional vibration is 0 is called as a node. In which shaft section there is 0 vibration amplitude, that is called as a node point. Here for the single rotor system, wherever that shaft is fixed, there will be vibration amplitude 0. Therefore this point we will call it as a node point. Now one node point is there and amplitude is there. This is called as amplitude diagram for that single rotor system, and this is a formula for natural frequency of single rotor system. Therefore we will solve one problem based on this torsional vibration. A shaft of 100 mm diameter and 1 meter long has one of its end fixed and other end carries a disc of mass 500 kg. Therefore diagram will be same as previous. One end of that shaft is fixed, another end carries a rotor or a disc 500 kg at the radius of gyration of 450 mm. The modulus of rigidity of the shaft material is 80 giganewton per meter square. Determine the frequency of torsional vibration. Now here we know the formula of single rotor system because here only one rotor, that is one disc, is attached to one end of that shaft. We know the formula for finding the frequency of such case. Fn is equal to 1 upon twice pi square root q by I, where q is equal to gj by L. Here in this calculation I have written, instead of g it is written c. Consider it as a g, modulus of rigidity, gj by L, where g is 80 giganewton per meter square converted into newton per meter square by multiplying 10 raised to 9. Therefore g into j divided by L, where j is equal to polar moment of inertia of the shaft, and it can be found by pi by 32 into d raised to 4, where d is the diameter of that shaft given in the problem. It is 100 mm. It is equal to 0.1 meter. Therefore we first found j, polar moment of inertia, then we can find out q, that is torsional stiffness, then we will find out I, that is mass moment of inertia of shaft, is equal to mk square. Then we can find out the frequency Fn is equal to 1 upon twice pi square root q by I, and the value we will get here is 14 Hertz. Pause the video and do the calculation once again on your own and see whether the answer is correct or not. Now thanks for watching today's lecture. In next subsequent lectures we will study the 2 rotor system and 3 rotor system as well as the problems based on that. So stay tuned. Thanks for watching.